Hi, welcome to Distinti's Rules of Acquisition, 4th edition. This is Rule of Acquisition 12, the Mathematics Fallacy. And Rule of Acquisition 12.0 is nature cannot be proven mathematically. Now, there's going to be certain people who are trained, physicists, whatever, engineers, who might take this back by this statement. Bear with me. I'm going to show you that mathematics is a great tool, but it does have limitations that we need to consider. Okay, there exists a false perception among scientists and engineers, and I've seen this, that mathematics is some secret language of nature. You'll often hear Brian Greene on any of the quantum mechanics things saying mathematics is the language of nature, things like that. You hear all kinds of quotes like that. Okay, and that's just not true. And again, we're going to get into that. Okay, and you know, they believe that if you could just get the right sequence of mystical symbols and numbers, that nature will do what you say and vast treasures will unfold before you. Okay, no, mathematics is simply a means to mimic nature, but it has limitations. And we'll get into that. Okay, one of the limitations are, and this is, ironically, it's not a limitation, but it's a limitation that it's something that needs a limitation, is mathematics is a superset of nature. It's possible in mathematics to derive phenomena which do not exist in nature. You have things like over unity, infinity, pi. Pi, yeah, we'll get to pi. I'll show you that pi cannot exist in nature in its perfect precision. Okay, so then that's why we get Rule of Acquisition 12.0. Nature cannot be proven mathematically because mathematics is a superset of nature, which means that it's possible to derive things that don't exist in nature. So in other words, if you come up with a derivation, you may actually come up with something that doesn't exist. And so if you're able to derive things that don't exist, then there's no way to use mathematics to prove nature. An example of a thing where people derive something that don't exist is in every electromagnetics textbook. It's a thing called internal inductance. If you look up the derivation of this, you'll find the derivation is perfectly done with the right mathematical procedure, but they failed to follow the laws of magnetism here. Okay, they did the math right, but they didn't follow the rules of magnetism. I have this in the foundation series where I do the derivation perfectly. And the worst part of it, they never bothered to go do they never bothered to verify this experimentally. They just assumed that if they could derive it, it must exist. That's wrong. They never bothered. I do a simple experiment in the foundation series where I show that this expression is complete nonsense. And it's in every textbook, and all these people just regurgitate in their textbook everything that came before, and nobody has bothered to check it. Why am I the guy that comes on? I don't know. Okay, and that's the reason why 12.2, all derivations must be experimentally corroborated. This isn't proven. This word means corroborate. This means that you say that it's valid. It doesn't prove it. It's rule of acquisition number 1. Okay, correct answers prove nothing. Okay, that's the first rule of acquisition. It's the first rule of acquisition for a reason. All you're going to do is corroborate that your derivation is consistent with nature. It does not prove that your theory that came to that derivation is true. The reason why is because nature is a superset. There may be multiple ways to arrive at the same conclusion. You saw that in Rule of Acquisition 14, which is also where we actually show that there's multiple different field geometries that could explain inductance. And that's also in the foundation series. Okay, so in this video, we're going to demonstrate that mathematics is an insane but very powerful and useful tool. Now, insane here, I'm using my definition of insanity, which comes from Rule of Acquisition 14, and we're going to go over that a little bit. But like any tool, it has its strengths and weaknesses. And I'm going to demonstrate at the end how the irresponsible use of mathematics has led to scientific stagnation and, in fact, idiocy. I've already shown an example just a few seconds ago, but there's more. So before we continue, I need the people that haven't already done this to go review the definitions. If you go to distinti.com, okay, somewhere down on the main page, there is a link for definitions. And the first 4 definitions in the list need to be gone over. And then if you haven't already seen Rule of Acquisition 14, I know Rule of Acquisition 14 is kind of a prerequisite to Rule of Acquisition 12, which is this, but they were kind of discovered out of order in the earlier generations of the Rules of Acquisition. And so I'm going to keep the numbers for whatever reason. Okay, and the 14.0 rule of nature is not insane. Okay, a sane system is deterministic, quantifiable, discrete, and causal. Insanity, from a scientific standpoint, not from a human insanity, from a scientific insanity, lacks any one or more of these. Now again, we're going to go over this in a little more detail, so don't worry. So if we do our sanity check, we're doing analytical, so we can break down mathematics into two different parts, analytical math and probability and statistics. Okay, those are kind of very broad, but they have their, those are the, and probability and statistics is what the majority of math used in quantum mechanics. And probability and statistics is indeterminate modeling. In other words, it doesn't give you an exact outcome of something. It gives you the best probability of where something is and what and what might be the. So in other words, it gives you a best guess of the future based on the past. Whereas analytical, it's more of a deterministic modeling. You can determine the future or the past with a knowable precision. And there really should be, there's a little bit of indeterminate, because with analytical math, you can do both causal and non-causal modeling. You can also do discrete and continuous modeling. And you can also do quantifiable and unquantifiable. It has quantifiable and unquantifiable traits. We're going to give you examples of these in a moment. Okay, and the insane elements, okay, the things I call insane, like non-causal, continuous, unquantifiable, are constructs that have no parallels in the real world. Okay, they have no parallels in the real world, because the real world, everything is discrete, quantifiable, causal, and deterministic. And I'm going to show you that quantum mechanics, which uses this indeterminate modeling, is incorrect. And I've had a number of videos where I've already shown that many of the things in quantum mechanics beyond Schrodinger's cat are just gone off the deep end. And we're going to get into some more of that here, so you don't have to worry about going back and finding it. There is one sane modeling tool. It's called a digital computer, because digital computers are deterministic, discrete, causal, and quantifiable. Now, some of you are saying, "Oh no, we can model things like infinity in a computer." No, you're not. You don't actually have a number that represents infinity. You have what would be equivalent of a digital symbol that represents infinity. There is no binary number that represents infinity. Okay, and the reason why a digital computer has to be all these things, because it's made of real stuff. Which are those things? If it weren't that, it would be insane. It wouldn't be in this universe. It would be scientifically insane. That's the way I'm using the word. So let's give examples of insanity of mathematics. This is an example of over unity. Now, if anybody says, well, this can't be true because A equals A plus 1, there's no way that that's ever going to be equal. Well, in the real world, absolutely right. You're absolutely correct. This would be an example of over unity in the real world. And we know over unity doesn't exist. Well, at least we've never seen it yet. Okay, let's just be fair about that. And so, for all intents and purposes, we could say over unity doesn't exist only because we haven't seen it yet. But I mean, the Big Bang might be the first example of over unity. Who knows? But let's just say, we haven't seen over unity. Let's say because we haven't seen it, it doesn't exist. Okay, but this has a real mathematical solution. Okay, the real mathematical solution, I'm going to divide both sides by A, which is equal to 1 equals 1 plus 1 over A. And so if I could make this go to 0, then I would solve the equality here. And the value of A that makes this go to 0 is the value infinity. Okay, and just like I stated previously, infinity is a value that we can't write down and we can't go measure it. It's not quantifiable. We can't go measure it. We have this symbol that we write which represents it. Okay, this isn't infinity. This is a representation of a concept of infinity that exists only in our mind. Now, somebody might say, well, we don't know if the universe is infinite. Well, I'll tell you what, you go out and go measure the length of the universe and I'll have your Nobel Prize waiting for you when you get back. If you think the universe is infinite, go ahead and try to measure it. Okay, so this is something we can do in mathematics that we can't do in the real world. And again, you can have infinite in your floating point processor in your computer. But again, just like this is a symbol that represents it, Okay, in your floating point processor, we have a particular defined binary pattern of the floating point number which represents infinity, but it's not the binary equivalent of infinity because you cannot represent infinity with a binary number. Okay, but there is a symbolic representation in your floating point processor. Pi. This is what they call an irrational number. Okay, an irrational number is a number you cannot represent in this universe, any way, shape, or form. It's got infinite number of digits. Now you might say, well, you know, an example of a rational number is 0.333333333 infinity. That can be rationalized as a ratio of 1/3. So even though we can't represent 1/3 in a decimal number or even a binary number, we can represent it as a ratio of two numbers. And that's what they mean by rationalize it, being able to represent something as a ratio. Pi cannot be represented as a ratio. It cannot be represented. It cannot even be written down. Again, we have a symbol that represents pi. And the best we can do in a digital computer is a good close approximation of pi that for all intents and purposes is good enough for anything we're going to do. Okay, so when you're using pi in mathematics and stuff, you're using a very close representation of it, an approximation of it, because you'll never ever be able to write the real number down in this world. And therefore, the only place it exists on a continuous number line. And therefore, because we can never represent this value in the real world, the idea of a continuous system is invalid in the real universe. It is insane. And it's also unquantifiable because you cannot measure pi perfectly. You can get a good approximation by taking the circumference divided by the radius of a circle, but you're limited by how precise your measurement instruments are, and you will never be able to measure it precise enough to get out to infinite digits of precision. Okay, so it can only be represented on a continuous, and because of that, it's not perfectly quantifiable. We can quantify it good enough, but not perfectly. So this value as represented by this symbol does not exist in this universe. All we have are things that are remarkably close to it and good enough close to it. Now, I'm probably going to get some mathematician that's going to come up there and have heartburn over that, but I mean, go ahead. Show me. I'd love to be proven wrong about things, because then I learn and I become better. Okay, and then you have non-causalities, and these mostly occur in probabilities. Like people, they have this thing in this commercial that says, people who vape are 4 times more likely to become smokers. I'm like, wait a minute. First of all, I have a problem because they never say 4 times more likely than what. So already it's a bogus statistic. But even if it weren't a bogus statistic, there's no causality here. You could easily say that, well, if there were no vaping, everybody that would have smoked, smoked. And because of vaping, some people that would have smoked did vaping instead, even though 1 in 4 or 4, whatever the ratio, some went to smoking. So you could actually say that vaping may have diverted some people from smoking if there weren't vaping. So there's so many ways you can twist these statistics around and come up with all kinds of weird causalities. The other one is, 95% of car accidents happen within 5 miles of the home. I mean, what? Is there some kind of monster that's creeping around your home that jumps out in front of your car causing an accident? No, there's no implied causality. This is all correlations, just correlations. And correlations are not causality. Okay, the causality might just be the fact that 90% of the time that you're driving, you're within 5 miles of home. And that's it. There may be no other thing to it. And that's why, because statistics can be so misapplied and there's all kinds of causalities can be inferred that aren't there. That's why Mark Twain said over 100 years ago that there are 3 kinds of lies: lies, damn lies, and statistics. And we're going to show that the use of probability in quantum theory has led them off the deep end. And then you have another thing that in mathematics you can have any number of dimensions, including fractional dimensions, whereas physicists believe, using the standard model, whatever the model is, that the real universe can be described in somewhere around 11 or 12 dimensions. Okay, so already right there, mathematics is such a fantastically big superset of what the universe is that you can come to any kinds of different solutions to the same thing. Now, So again, 12.1, math is a superset of nature, which means that it's possible to derive things that do not exist in nature. And this is where Tesla has said that today's scientists have substituted mathematics for experiments, and they wander off through equation after equation and eventually build a structure which has no relation to reality. Absolutely true, and we're going to show you examples of that in quantum mechanics. But that doesn't mean throw out your textbooks, because he also said his, meaning Thomas Edison's, method is inefficient in the extreme, for an immense ground had to be covered to get anything done at all, unless blind chance intervened. And at first, I was almost a sorry witness of his doings, knowing that just a little theory and calculation would have saved him 90% of his labor. Okay, so just because of the drawbacks of math, it is very powerful. It can save us lots of time making things efficient. So you cannot have theory without math. They have to go together, but you have to corroborate with experiment to keep you from going off into the deep end. Okay, and math is actually a merger of the sane and insane components. It can be both or the same, and you have to take the sane and try to get rid of the insane. So we should always strive to use the sane constructs of mathematics, but there are times we have to use the insane constructs. Okay, and we'll show you some examples of that at the end. But as long as we do not attribute any of the insanity to modeling tools to nature, and this is from Rule of Acquisition 14.4. Now, for Rule of Acquisition 14, I have an errata, a change. After doing this one, I realized I made a mistake in the 14th Rule of Acquisition 14. The way it is now is nature is not insane. Insanity can't be modeled or predicted, thus it has no practical application. Well, I'm already saying right here that insanity can be modeled, so that's not true. That's got to be removed. And the revised one is 14.0. Nature is not insane. Insanity is unpredictable, having no practical application. And so that's the revised 14.0. Now, this is interesting because in the early days of quantum mechanics, you had things like the Balmer series, which showed that the energy levels of atoms are very discrete. So we're showing discrete here, discrete quantities of energy, and they don't go into any energy levels in between those. It's just these levels. So there's no continuity. It's discrete, and it's very causal. It's very deterministic. Okay, so everything about the early days of quantum mechanics, and the name, because the little quantas of energy, the very discrete packets of energy, those quanta of energy, that's where quantum mechanics gets its name. This looks just like binary math on a computer. Okay, where the binary numbers either take 0 or 1 or nothing else. Nothing in between. So this is looking remarkably like a very deterministic system, as like a digital computer is. And the thing is, how we went off the deep end. And let me show you the pseudo-insane demo here. This is the demo from Rule of Acquisition 14. I'm going to do it again here. Here's a deck of playing cards. This deck of playing cards is discrete. It's causal. It's what's the other ones? Quantifiable. There's quantities. And it's deterministic. I think I got all 4 of them. Okay, so if I had perfect knowledge of the order of the cards in the deck, and you and I were to play blackjack or poker or whatever, then I could do my betting with very precise knowledge of what cards you have, what cards I have. And therefore, using this deterministic system, this sane system, it's got to be sane because it's made of nature, I could bet very deterministically and clean your clock, unless you knew the order of the cards too, then it would be, whatever the order of the cards are. Okay, but now if I lose information and I shuffle this deck of cards, okay, that means now I lose the information. I've lost information. The best thing I can do is use an indeterminate modeling, an insane modeling technique called probability theory, probability and statistics. Probability and statistics is insane, but it's the only thing I have when I've lost the information of the order. And so the argument I made in the 14th Rule of Acquisition, you can only apply probability theory to a sane system when you're missing the information about it. And that's what happened in quantum mechanics. We don't know much about what's going on the underneath and all this stuff. And so the best we can use is probability theory. And it worked very good. In the early days of quantum mechanics, we did things like noise analysis, semiconductor modeling, wells and all that stuff. And it worked great. We're still using a lot of that stuff today. Because those things all made deterministic declarations of what the underlying system was. Like in noise. We just assume that there's a whole bunch of little oscillators in discrete energy bands and stuff like that. And then we integrate them up probability theory, and we come up with very good models for noise using probability theory and probability distributions, the whole 9 yards. All those things work great because we make the determination that the underlying system is sane. It has all those 4 properties we talked about. And that's where it's good. The problem is where we went off into the deep end, right after Schrodinger's cat. And we're going to get into that next, I think. Yes. So in Schrodinger's cat, they did this thing now. Instead of using probability distributions like we engineers have been using for a long time, and it works great because probability distributions make the assumption that everything underlying our probability application is sane. Okay, but somewhere along the way they said, okay, here's the cat. The cat is in the box. Is the cat alive or dead? Because they put a little poison thing that's going to go off using some kind of radioactive decay. And so there's a 50% probability the cat is alive or the 50% probability the cat is dead. But because we don't know the information, we have to use probability theory. Okay? That's all it boils down to. We're missing information. But if the cat breathes the poison, the cat's going to die. Now they're saying that the cat is in a superposition of states where it's both alive and dead at the same time. In reality, are you ever going to see a condition where a cat, maybe it's a zombie cat that was buried in a pet cemetery somewhere where it's a living dead. Okay, that's where I think quantum mechanics, they buried their cat in the pet cemetery, and that's where quantum mechanics went off the deep end. Because here's a problem with that. Okay, what I'm going to do here is I'm going to take 10 red cards. 1, 2, 3, 4, 6, 7, 8, 9, and take 1 black card, okay? So I've got 9 red cards. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 red cards, 1 black card, okay? So I'm going to shuffle up these cards, okay? And I'm going to put a card here and a card here. The odds that any one of these cards is a black card is 1 in 10. Now, when you're using the superposition, the probability superposition, you get into a weird conundrum. Because this card can be all of the cards simultaneously. That's what they say. That's what they say. There comes the odd possibility that both cards are black at the same time. But you're looking at me like, Bob, you're nuts. You only have 1 black card in there. But that's not how they use the math. Because they have this superposition and they're simultaneous. Okay? It's the possibility that both of these cards are a black card at the same time exists. And that's where they come into the bullshit. That's where they're applying the insanity of their modeling tools to nature. Because you and I both know, okay, that if there's a black card on here, it can only be 1, or if the black card is in my hand, it's not. So, because I saw this now, that the black card's in my hand, that we know it's 0 probability that that's a red card. And I don't have to look now. So these cards aren't spinning through a superposition because they say, oh, you've collapsed the probability superposition. I mean, what a load of nonsense. Okay, these cards are not abiding by that math. And that's where I get into problems because quantum mechanics talk in terms as if the math is causing nature to do this stuff. It's not. The math is just a very human way to mimic what we observe and nothing more. Nature is not obliged to follow our silly imaginary mathematics. But if our mathematics has to be valuable, our mathematics has to properly mimic nature. That's the duality. Okay, so right there you see that because of this thing that they do, saying, well, the probability that, if I knew one of these were a black card, let's say, then we could say, well, there's a 50-50 probability one's black and one's red. and the probability that two of them are black at the same time because of the superposition. And that's where they get into all this stuff about parallel universes and all that stuff. They've attributed the insanity of their modeling tool to nature. Okay, and let me show you another example. Let's say, let me actually take out the black card here. So we got a black card and a red card. Oh, black card and a red card. Now I'm going to shuffle these up. Okay. Now I'm going to split these across the universe. Because right now, using their stuff, this could be a 50-50 probability of being a black or a red card, and that could be a 50-50 probability of being a black or a red card. But now I'm going to put these at one side of the universe and that on the other side of the universe. And this is what we talk about quantum entanglement. So if I observe this, okay, right now their probability is 50-50, 0.5. But if I observe this card, it's red, that means its probability goes to 0 and its probability goes to 1. And that's where the black card is. So I could say those cards are entangled. That's the bullshit that they come with. They've applied how the probabilities changed. They've assumed that these probabilities changed because I observed something. The cards didn't change because I observed them. This card that's there is still there when I first put them down. And because the probabilities change, they're applying that saying nature is changing. And that's the bullshit that's going on. Okay? Quantum mechanics in the early days was great because they made the determination that the underlying system was deterministic, causal, and they're just missing information, and they're trying to fill in that missing information using probabilities. And that's fine. We still use that today. Matter of fact, I have found out that quantum computers, I've done a little bit more research, are actually being based on Balmer. There's a thing called a quantum dot. And this is what you're going to get in a quantum computer. It's not going to be the probability superposition where they're claiming they can do all of the different states simultaneously. That's nonsense. And it's not this baloney of quantum entanglement where you're going to have tangled qubits. And oh, that's all gibberish. You're actually going to get something that is from the early days of quantum mechanics. It's quantum dots work on this theory here. And so all they're doing is making a computer using very, very small, discrete things. It's like a binary digital computer, but it's going to be very, very small constructs. And that finally explains to me why they need all this error correction. Because when you're working down at the scale where this is true, it's very susceptible to all the influences around it. It's very corruptible. And so I got a feeling is once they add in all the error correction, you're not going to be able to get anything much better than what we got already with the standard digital computers. So the quantum computers you're getting are just a smaller scale normal computer that might be trying to take advantage of these very discrete states, but it's really not going to give you anything better than having binary discrete states from digital logic circuits. And as a matter of fact, it's going to be, rife with noise. So that's what you're really going to get. You're not going to get all this spooky action at a distance nonsense. All that stuff I've just proven in my T8, T12, and I'll put the links in the low bar. Okay, so now again, for those who don't know about the rules, I've concluded that the human brain is easily distracted by nonsense, making clear logical thought difficult. The rules of action provide a framework of tells, traps, imperatives, paradigms, which help overcome groupthink, false truth, tribal superstitions to improve the scientific method. For example, the false notion that experimental corroboration proves a theory to be true, this is rule of acquisition 1, is a clear example why scientific method is deficient and requires a more robust framework in which to judge scientific theories. Okay, and a restatement of the mathematics fallacy. 12.0, nature cannot be proven mathematically. 12.1, mathematics is a superset of nature, which means that it's possible to derive things that don't exist in nature. And that requires 12.2, which all derivations must be experimentally corroborated. Again, this is not proved. This is just corroborated. It only means that your model mimics nature. It doesn't mean your model proves nature or nature proves your model. There's no proving going on here because there could be other ways to get to the same answer from a different means. And then from that, because of that, 12.3, expect the existence of different ways to mathematically arrive at the same result. This is based on my idea of polytheism, which I believe is in the first rule of acquisition. Okay, and again, 12.4, math contains both sane and insane constructs. And you can go to Rule of Acquisition 14 for the definition of scientific insanity. Okay, and in the Rule of Acquisition 14.4 is do not attribute any insanity of the modeling tools to nature. Okay, modeling tools are going to have insanity because they're a figment of the human brain, except for digital computers, because they have to be built from real things in the real universe and not be built from the stupid stuff in the human brain. Okay, so part of the rules of acquisition here is to eliminate the insanity from our models and theories that come about from our flawed or I don't know if I want to say flawed. I mean, math is a superset. That really may not be a flaw. That might be an advantage. Okay, but we can't attribute the things, the insane parts of mathematics, to nature. Thank you, and thank you for all my Patreon people for being... Anyway, I'll have a separate thing for you guys, explain what's going on. Thank you very much.